Hi everyone, and welcome to Lesson 2, Video 1, Graphical Analysis. There are going to be two videos in this lesson. The first video is an introduction and theory video. The second video will focus on providing worked examples. Graphical analysis allows us to take two variables and determine if there's a relationship between them. By the end of Lesson 2, Graphical Analysis, you should be able to create a scatter graph for data. You should be able to verify a supplied relationship between variables. You should be able to manipulate raw data according to a given relationship so that when plotted, the manipulated data creates a linear graph. And finally, you should be able to read a gradient and a y-intercept from a linear scatter graph. In this video, we're going to have a quick revision on the types of variables. Then we're going to look at the relationships between variables. We will discuss how graphs can help us to visualize the relationships between variables. We will see that not all relationships between variables are linear in Year 11 physics. The good news is that we are only interested in linear graphs and interpreting linear graphs. So in those situations where the relationships between variables are nonlinear, we will learn the skill of manipulating raw data such that it gives us linear graphs. Finally, we will use the linear graph to find a quantity. So before we go any further, it's time for us to revise variables. When you hear this word variable, you might think about lower school investigations and how we always looked at independent variables, dependent variables, and controlled variables. There is always one independent variable, there is always one dependent variable, and there usually be quite a few controlled variables. Variables themselves are things that we observe and record for an object or for a system or for whatever the thing is that we are studying. Variables themselves break up into two broad categories: quantitative and qualitative. Quantitative variables are those variables that involve value, magnitude, quantity, measurement, numbers. Qualitative variables are those variables that involve description but not measurement. Quantitative variables break up into discrete and continuous variables. If we were surveying students on the question of extending the lunch hour and then also extending the school day, we would see that students would fall into two camps, yes and no. And that would be a discrete variable because you can't have half a student in one of those columns. You might have 60 students in the yes column, 240 students in the no column, but you can't have 60.5. Continuous variables are those variables where the value of the variable could be any numerical value, any real number. Continuous variables are the variables we are most interested in Year 11 physics. Qualitative variables fall into two camps, nominal and ordinal. Nominal variables are observations of the subject which were simply descriptions without any relation to each other. Postcode, state of origin, blood group, these are examples of nominal variables. Ordinal variables can often be fielded upon a spectrum, and you most often see ordinal variables in surveys. Some surveys, they ask you to tick a box on a spectrum based on your opinion of an idea. Strongly disagree, disagree, undecided, agree, strongly agree. Each one of those can be thought of as an ordinal variable because they clearly have a place in a spectrum, but we don't measure them. As I said previously though, in Year 11 physics, and particularly in graphical analysis, we are most interested in continuous quantitative variables. In physics, we observe the world around us and we record these observations in our notebooks and we refer to these observations as variables. We are interested in continuous variables for the most part in Year 11 physics. Continuous variables for us in physics is anything that you can measure. Now, I don't know if you did this, but a very common experiment that we do in Year 7 science is to observe a candle. It's a little game that we play, a competition. We give Year 7 students a candle lit on the table in front of them, and we ask them to write down a list of all the possible things that they could measure and observe on that candle. I've written a couple of examples down. We could measure the height of the candle, the diameter of the candle, the mass of the candle, the density of the candle. Continuous variables are all around us. And it just takes our imagination to look around us and see what is it we can observe and what is it we can measure. Take a moment, pause the video, and write down a few other things that you could measure for a lit candle, and then play the video on. The real power of physics can be found not in the variables we record, but in the relationships between the variables that we record. If you can identify a relationship between two variables and transform that relationship into a mathematical equation, then you can make predictions for what the variables will be in some region where you've not yet done measurements. This is the heart of what leads towards scientific laws, and it's the real power of physics. Here's an example. We've got a car traveling down the freeway, and we take observations of the car as time passes. We've collected these observations, these two variables, time and distance, in the two columns in this screen. We see time is in minutes, distance is in kilometers. And what we can see is that as time passes, the distance increases, and it seems to be increasing by the same amount each time. And as we take our measurements from 0 minutes, 6 minutes, 12 minutes, we notice that the distance goes up from 0 kilometers to 10 to 20 kilometers. So we can see from the table quite easily that distance is proportional to time. There is a relationship there. You can probably tell from this very simple example that it's a linear proportionality, a direct proportionality, but that will not always be the case. There are many different types of relationships between variables. The relationships between variables might be proportional, so that if one increases, the other increases. The relationships between variables might be inversely proportional, so that as one increases, the other decreases. If there is a linear proportionality between the variables, then we'll be able to plot the raw data and see a straight line on the graph. But often in Year 11 physics, we'll be dealing with non-linear proportionalities. With non-linear proportionalities, when you plot the data, you don't get a straight line, you get a curve. And what this means is that the equation for the proportionality involves one of the variables being raised to a power. People doing research have to figure out what the power is. But the good news is, for us in Year 11 physics, we will not have to do that. For us in Year 11 physics, we're always given an equation showing the relationship between the two variables. Our task then is to take the raw data, manipulate it in a way that is consistent with the equation, plot the manipulated data, and hopefully see a linear graph. Here is an example. Imagine that we drop a marble from a hot air balloon very high up in the air. It's a bit of a silly example because I'm not sure exactly how we'd collect this data, but just accept it for now. We've collected the data of time in seconds. We've collected the data of distance fallen in meters. We can see that these two data sets are proportional. As one gets bigger, the other gets bigger. But when we plot them, we see that it's not a linear proportionality. We want a linear proportionality. You might remember that the equation for a linear graph is y equals mx plus c. In trying to solve this problem, we are given the equation s equals a half at squared, where s is the distance fallen, a is the acceleration, and t is the time in seconds. If we put these two equations underneath each other, we can see visually that they have a similar shape. Y equals mx plus c has two variables in it, y and x, and two constants, m and c, where m is the gradient and c is the y-intercept. S equals a half at squared plus 0 has two variables in it, s and time squared, or the square of time. It also has two constants in it. A half a is one of the constants, and the other constant is 0. If we want to manipulate the raw data such that we can graph a linear graph, all we need to do is transform the time data into time squared data. If we plot on the y-axis the distance data, and if we plot on the x-axis the time squared data, then we should get a linear graph. Having created our linear graph by plotting distance data on the y-axis and the square of time data on the x-axis, we can now figure out the acceleration of the marble. In the linear equation y equals mx plus c, m is the gradient of the graph. So the gradient of the graph of a marble drop from a balloon, where we have distance on the y-axis and the square of time on the x-axis, the gradient of that graph is a half a. Using the magic of Excel, I can say that the gradient of the graph is 4.9 meters per second. In Year 11 physics, you won't be able to use Excel to do that most of the time. You'll have to do a rise over run calculation. But because we know that the gradient is 4.9 meters per second, then we can say, right, 4.9 meters per second is equal to a half a. Therefore, a, the acceleration of the marble, must be equal to 9.8 meters per second. This brings us to the end of Lesson 2, Video 1, Graphical Analysis. So what now? Take a moment to jot down the ideas from this video in your physics notebook and try to do it from memory rather than going back through the video and just copying things down. Then, you might read and take notes on Appendix B of the Pearson Physics Year 11 text. It would also be a good idea to complete the Chapter 1.3 questions from the PDF titled HP Chapter 1.1 to 1.3, which you can find in Sector. If all of that is done, then it's time to view the next video in this lesson, which focuses on graphical analysis examples. I hope this was useful.